Hello, quantum explorers.
And friends of the environment?
The environment, cool. We will indeed be talking about the environment today and how emerging technologies such as quantum computing could help make our world a little bit more sustainable. Hi, I'm Katya Moskowitz, science communicator and theoretical physicist.
Hi, I'm Kai, the quantum kid, and I like being nice to the environment. And today we are going to be talking about the environment with two amazing guests. And drumroll, Stephen, Chu, and Peter Shor.
Exactly. Indeed, we have two amazing guests joining us here today. Professor Peter Shor from MIT, who in the 1990s developed a really cool quantum algorithm called Shor's algorithm to show that a quantum computer should be able to factor really large numbers much better than a classical machine ever could. And by the way, that also shows us that a quantum computer poses a really real risk to currently used cryptographic systems, such as RSA, for example. And also joining us here today is Professor Stephen Chu, Nobel Prize winning physicist and former US Secretary of Energy, who is currently working at Stanford University, leading efforts into clean energy and discovering technology to slow climate change. Welcome.
Thank you. Hi, Kai. Hi, Katya.
Thank you so much for joining us today. So we will be talking about sustainability, about quantum computers. Kai, you had a really good example about the environment, right?
Yes, so in Easter Island, there are a lot of statues, and also there were a lot of forests, and those forests disappeared from Easter Island from some weird reason. And here, I'll show you. This Easter Island. Look at those cool statues. Let's go closer. Hundreds of years ago, the people of Rapa Nui, a tiny island in the South Pacific, also known as Easter Island, carved these incredible stone statues. When those people first arrived here by boat from Polynesia, the island was covered in trees. Over the centuries, those forests largely disappeared. People used some wood, of course, but even more importantly, the rats. They brought along with them, ate palm nuts and seeds, and stopped new trees from growing. The islanders adapted, but the forest ecosystem collapsed long before any outsiders arrived. Rapa Nui's story shows how quickly human choices and introduced species can upset nature, a warning we still face today with deforestation and climate change.
Deforestation is a big problem as well today globally. So, Professor Chu, in your opinion, what lessons can we draw from Easter Island's story as we trying to develop new technologies, including quantum computing, to address sustainability issues?
Well, I'm not an expert in Easter Island, but certainly it is well known when people settle places, they might clear forests for agriculture, and humanity all around the world has been doing that for quite a long time. In the U.S., which I know a little bit more about, this certainly happened in the Middle West. There were lots of forests that were just simply cleared for farming. Also happening in South America to grow more soybeans for animal feed, things like that. Lots of forests have been cleared.
Yeah, so will the world later look like a futuristic place with where you just step on a train then starts flying you to your house, or will it be like a dead wasteland where no trees are there anymore, or lakes, everything dried out?
Well, something in between. I think the danger of forests, especially old growth forests and natural habitats, is there are two things. They are a big storehouse of carbon, and they're the bone marrow, if you will, of diversity on the planet. And so when we destroy these old growth forests, we're really destroying a lot of what has really contributed to the diversity on Earth. Forests do capture a lot of carbon, especially growing forests. Mature forests is a very, very different story. And so are attempts of reforestation, but you also have to encourage the people in those countries that they can make a livelihood without deforestation. And in limited programs, that does work. And I think in general, the environmentalists around the world recognize how important these forests are to the health of our planet.
I also saw on a video once that we get oxygen from trees because they take all the carbon and then they give out the oxygen to us.
Well, you're absolutely right that photosynthesis, for when the Earth was formed, the oxygen elements in the Earth were tied up in other things, and molecular oxygen, the stuff we breathe, was not in the atmosphere. And so what happened is photosynthesis, there was a lot of carbon dioxide in the Earth at the early Earth, and converting that to oxygen. And so this happened beginning a couple of billion years ago, and there was if you look at that time history of the 4.5 billion years of Earth, all of a sudden there was an uptick in oxygen when photosynthesis, starting with microbes, not trees, began to flourish. And this is what we breathe. Without that photosynthesis, animal life would simply, and people like us would simply not be here.
Yeah, thank you for that. Professor Shor, in your opinion, how could quantum computers help us when it comes to the environment?
Yeah, quantum computers are not based on bits, which can either be 0 or 1, like ordinary computers. They're based on qubits, which can be in a superposition of states, so they're essentially 0 and 1 at the same time. And the way that quantum computers can solve problems more quickly than classical computers is they can do all sorts of different computations at once. And then to get the answer out, they interfere these different computations. So they take all the paths that lead to the right answer and interfere them constructively. So the probability is much larger than it would be otherwise. And they take all the paths that lead to wrong answers and interfere them destructively so that their probability of seeing them is much smaller than it would be otherwise. One of the things quantum computers are really good at is figuring out what quantum mechanics says molecules will behave. So if you want to see whether a potential compound is good for something, say catalyzing a reaction that takes carbon dioxide out of the atmosphere, you can do that much faster on a quantum computer than on a classical computer. So quantum computers are good for exploring new materials, and the right materials could really help with the environment.
So could a quantum computer help, like, save the environment, really?
First of all, computation, whether classical or quantum, isn't going to save the environment. It's going to be people who realize that what we're heading for is very dangerous territory and huge risks to society. And convincing people of that is very different than any computation. Over the last decade or two especially, virtually all the serious scientists who've studied this say that the risks of a changing climate, risks where we go to 3 or 4 degrees centigrade compared to before the Industrial Revolution, could have devastating impact on the livelihoods of people around the world. For example, one could expect collapse of local agriculture. And when that happens, what we see in developing countries is a potential collapse of the whole civil order. And when that happens, people get desperate, they migrate, the whole civil order disintegrates. Historically, that has happened 1,000 years ago in the Middle East, the destruction of the Babylonian Empire. And so if the climate models, which have large uncertainties, but if there's this long tail risk, where it is possible that you could actually have parts in the world collapsing and perhaps the richer countries not being able to help. So that's a start. But the short answer is these computers are a tool. They help us see forward. They help us with finding solutions. But in the end, it's the people who have to make this choice.
Yeah, so what we know quantum computers are good for is they're good for certain number theory problems, which you could use to crack all the cryptography that's widely used. They're good for simulating quantum mechanics, which would really help immensely in designing new materials. And new materials could be very useful for solving the climate crisis. There are some signs that they're good for optimization, which again is a very useful thing. But the optimization programs we know how to use on quantum computers are really fairly limited so far in what they can do for most optimization questions. We don't know how to speed things up with quantum computers yet. So optimization is really good. You can ask, what's the best way to do something? What's the best way to change all the agriculture so that we can be protected against risks from climate so that we can ensure that we have enough food to save people? So that's a really complicated optimization problem. And right now, it's not clear that quantum computers are better at that, but they're better at some optimization problems.
Right. And what about simulating systems? They are good at that too, right? So, for example, if we go back to the story of Easter Island, when Polynesians first came to Easter Island many, many years ago, they brought rats with them inadvertently. And the rats then ate a lot of these palm seeds and nuts and so on. So the forest gradually disappeared. In your opinion, would quantum computers also be good in simulating such events when there could be a potential ecosystem collapse due to deforestation and other problems, other challenges that we are currently facing? Could they simulate those scenarios ahead of time?
To simulate a scenario, you really need the right input conditions and facts. So, for example, if you were trying to simulate what happens when you introduce two rats to Easter Island and you didn't realize that rats really liked the seeds that trees grow from, you would not get the right answer. So I think it's much more important that you get all the parameters right in your simulation than whether you can simulate it. Simple simulations, a classical computer can do really easily, and it would have to be an incredibly complicated scenario to simulate that you'd need a quantum computer. And if you have an incredibly complicated scenario, you've probably got some of your parameters wrong, and you might easily get the wrong answer.
So could today's technology fight the climate change? How today's technologies would be helping?
Well, certainly there's places where we can use much better technology. We've made great strides in, for example, harnessing the sun with solar photovoltaics. But let me give you an example. There's a new type of class of materials called perovskites. They're very complicated materials, and they can also, in conjunction with silicon photocells, improve the efficiency of converting sunlight energy into electricity by almost a factor of 2. But there's a problem. These materials don't last very long. They're lucky if they last a year. And we would like them to last in sunlight for 20, 30 years. Silicon now lasts 30, 35 years. And so it's a materials problem. It's a complex quantum mechanical problem, because these are very complicated materials. And I don't think conventional computers are going to find a way. So what material scientists do is they say, look at how they age. And they see grain boundaries moving. And they try to freeze in the grain boundaries. And one hopes that quantum computers can help us discover entirely new classes of new materials for solar. But there are all sorts of material issues. For example, we don't talk about this very much, but if we begin to electrify, as we should in order to clean up our power system, we're going to start to run out of copper. Not anytime soon, not in 50 years, probably not even 100 years. And what happens when you, quote, run out is the price of copper goes up, and then it can stall this transition to a more electrified future. Could we design carbon materials in order to have the conductivity and its conductivity per weight ratio of copper? There's existence proofs like carbon nanotubes and graphene that have that conductivity, but I don't know whether computers, either quantum or classical, can actually help us synthesize these materials so they're inexpensive, because that's what we need. You can make stuff in the laboratory and it's great in little gram quantities, but that's not going to change the world. And so if you look at the progress in all the industrial revolutions, the semiconductor revolution, these actually start with materials problems and how do you make materials pure and inexpensive. And it includes transistors, includes optical fibers and optical fiber communication, batteries, which will play an essential role in the coming decades and centuries. And how do you make them better, safer, and less expensive? Quantum computing is best at doing quantum mechanics, and the materials are essentially quantum mechanical.
Quantum computers are really too small right now to do much of anything. Until a month or two ago, the largest quantum computer was maybe a couple hundred qubits. Now they've figured out how to build quantum computers of 1 or 2,000 qubits, which is a much bigger. But the estimates are that to do anything interesting, you probably need at least 100,000 or 1,000,000 or 10 million quantum bits. So it's still going to be several years before we get quantum computers that will actually help solve problems.
But progress is rapid. A former postdoc of mine started a quantum computer company based on laser-cooled atoms and optical tweezers, what I got my Nobel Prize for. And they're pushing 10,000 qubits now. They can pick up individual atoms, huge arrays of them, pick up individual atoms massively parallel, put them into atomic states where they interact with each other quantum mechanically and make the states stable enough so you can go through dozens of, and really you need to go through hundreds of quantum cycles and real error-corrected qubits. You got to be in the 10,000 before things get interesting. 1,000 is a minimum. And with today's technology, as the error rate gets down, you need fewer quantum bits to make a real error-corrected qubit. Progress on the hardware side is advancing very rapidly.
Yeah, to do anything with qubits, you need to error correct them. And we know how to error correct them, but we don't know how to error correct them very efficiently. And looks like there are enormous advances in the best way we know to do error correction in quantum bits, and that is going to really also speed up the development of quantum computers.
Right. And what about the use of AI? Right now, we are already using AI, of course, for sustainability, climate research, and so on. So would you say that together with quantum computing, things will get even better in terms of using new technologies for sustainability purposes?
Definitely. There's a dark side to this. AI is turning out to be useful for a lot of things. So companies like Meta and Amazon and Google and Microsoft are putting in huge, what we call our exascale compute machines. These machines gobble up a lot of electricity, hundreds of millions of watts of energy running 24/7. But the new generation, for example, AWS, they're going into the billions of watts range. There's rising concern in the US, for example, that this huge demand of energy, electricity, is driving up prices. That presents a dilemma. This huge demand of electricity, what people are finding is, oh, if that's good, and make it increase by tenfold, make it increase by 1,000-fold. Unlike conventional computers 20 years ago, when they got good enough that what is now in your laptop or your desk can be faster than the fastest IBM computers. Well, for these applications, at least for the short term, couple of decades, the appetite is insatiable. And not all that electricity is carbon-free as well.
Right. And so we were talking about materials before, and just got me thinking, Kai, you always complain about batteries, right? When batteries died, for example. So that could be another way quantum computers could help, because they could help us design new batteries. Would you like that? What do you think?
Yeah, because I like the idea of electric cars because they have big battery rechargeable. But if you recharge it too much, then it breaks down in some way, and that leaves waste that's bad for the environment. So that's I would love to change.
All these problems are solvable. One of the chief engineers of Tesla has broken out and started maybe 8 years ago a new company to make the electric vehicle batteries much more recyclable. And a Tesla battery now, it doesn't make any economic sense. But there's another thing about batteries. People constantly worry about them running out, things like that. The energy per unit volume and the energy per unit weight of batteries has doubled in the last decade. The very best batteries used for lightweight things like drones are really changing things. And they could double again. It really depends. We're very far away from the physics limits, but it becomes materials problem design. And if quantum computers end up doing the quantum mechanical stuff much faster, that would be great. Right now, we discover new batteries by what I call shake and bake methods. You just try it and see if it works. Stick it in the oven, see if it works. It doesn't.
Shake and bake.
So
That's good.
Shake and bake. Shake and bake.
Professor Shor, would be interesting to see in terms of specific technology applications of quantum computing for batteries. Where are we right now? Is anything already happening? Where are we in that research?
I don't know if anything's happening, but really the reason nothing is happening is because our quantum computers are not big enough yet. But they've gone up at 10 times in the number of qubits over the last year. If we see this rate of progress, in 5 years, they'll be big enough to do all sorts of interesting things.
What would you recommend for kids who want to go into sustainability and at the same time make use of the new technologies like quantum computing? What would be the pathway for young people to get there?
Well, I mean, they're going to have to study physics. I guess they're going to have to study environmental sciences. It might be useful to study some computer science, and that's probably more than enough for 4 years of college. So the problem with quantum computing is the amount of stuff you have to know to be an expert in it.
there are many, many problems that need to be solved. And prejudice, you start with physics. And because if you understand undergraduate physics very well, very intuitively, for virtually all the applications in the world, that's all you need to invent something new. It's not the advanced physics with lots of complicated equations that's where things start. It's with some picture in most people's minds, some mental picture of something. And most of what happens ultimately could be understood in terms of freshman, sophomore physics. I mean, it's a very famous physicist, Richard Feynman, said that many, many times while he was alive. In fact, he was really revered among his faculty members at Caltech. They wanted him to give a seminar on some new development in physics. And so after a month, he said, I can't give the seminar because I have not reduced it to freshman physics yet. So I'm still struggling with trying to understand it.
I also heard that Richard Feynman said that if you know quantum physics, then you don't know quantum physics or quantum mechanics.
Well, it's a funny subject. Physicists learn how to use it, but there are very unintuitive aspects of quantum mechanics. And unintuitive, it doesn't kind of make sense to us intuitively that you can take something, some state of atoms or photons or whatever, you can separate them. So you put them many light years apart. And then quantum mechanics says, I make a measurement over here, let's say the polarization of a photon, then I know what's over here. Now, at first, that's not a big mystery. Suppose you had a single state of white marble and black marble and separate them. Then if you see white on one side, you'll know you see black on the other side. But quantum mechanics is weirder than that because you can decide how to make the measurement. So you can measure white and black, or you can measure red and green, or you can measure any other pair in some complex space. And you can decide what you want to measure over here in one galaxy, and then that will affect what you're going to measure in the other galaxy. And if you decide how you're going to measure the quantity, black, white, red, green, it's still a very correlated, a completely entangled state. So that's the weird part about quantum mechanics. That makes no sense to normal people.
And Richard Feynman also says that you can understand what quantum mechanics does, but if you try to understand why it does this, you will go down the drain and get stuck in a conundrum that nobody has ever come out of.
Yeah, and people have tried since the birth of quantum mechanics. In 1925, it was officially considered the birth of quantum. Here we are, 100 years later. And, there are these aspects of quantum mechanics that the physicists are saying, well, I don't really understand it. I know how to do the calculation. I can solve problems with it. But, so in that sense, we're just mechanics.
Thank you so much for joining us, Professor Shor and Professor Chu. I hope that everybody will start taking care a little bit better of our environment because we've only got one world. And as we said earlier in the show, it's not just the technology, it's the people that really can make a change, right? So thank you so much for watching us today. Please don't forget to like us and subscribe to the Quantum Kit for our future episodes.
Thank you.
Thank
Thank you.
you, Kai. Thank you.
Bye-bye.